Okay, I just started recording. Seems like it's working. Okay, sorry. The first little bit is not recorded. Okay, I hope it works. Uh, so lecture videos are recorded, so class attendance is encouraged but not mandatory. So here's the tentative weekly lecture schedule. Week 1 is an introduction and a broad overview, a broad review of the field. Week 2 is on functional safety and ISO 26262, the safety certification standard, and also perception and sensor fusion algorithms. Week 3 will be on motion planning. Week 4 is control algorithms, including PID and PC. Starting from week 5, we'll delve into reinforcement learning. So weeks 5 to 7 will be taught by Carla, including introduction to RL, deep RL, and also application of RL to autonomous vehicles. Week 8 will be a discussion of latest research on RL for autonomous vehicles. So this schedule is still tentative. I'm still working on the slides. It takes a lot of time, so there may be slight deviations, but the general framework is like this. So I was initially I thought I'd focus on the reinforcement learning approach, but later I realized that IR for autonomous driving is primarily at a research stage. Industry relies on the classic pipeline. So to make this course more relevant to industry, I added a little bit more material on the classic pipeline. Uh, so this link, box link, is where all the lecture slides will be put. So please bookmark it. I may upload slides, update slides slightly after each class if I find any mistakes. So it's more convenient to put them here. So I see a little bit mistake. Okay. So you guys can look at the slides now, right? So please download the slides, and so you can refer to the slides when you ask questions. I updated the slides last night, I think. So also this morning. So please download them if you did it earlier. So the lab sections will be based on Ducky Town. It is both a simulation environment and also they have physical robots, mobile robots for competitions. So it actually uses OpenAI Gym in the backend for its algorithms. So more details will come in later weeks. Labs will consist of control algorithms like PID, MPC, and the various reinforcement learning algorithms, DQN, DDPG, A3C. So we haven't decided which ones to include yet, but they're more or less all similar. So for controlling a car in the simulator, we're not going to have physical labs. We're not going to work with physical robots. So I will try to keep the project size small. If it's deep reinforcement learning, it's not really deep. It's probably 2 or 3 layers of neural network. So you can work on your laptop computer without powerful GPUs. So due to social distancing, there will not be access to on-campus labs, nor physical office hours. A great distribution is a final exam 70%, lab sections 30%. Final exam will be open book. because for a distance exam, it's not realistic to have closed book exams. So I haven't decided the exact form of the exam. I may just email a Word document at the exam time, or I may use the quiz functionality in Canvas. In any case, the exams will be mostly multiple choice or quick, short Q&As type of questions. So before I go into today's technical part, are there any questions on the logistics? Okay, so I see you are all, so can you unmute yourself, or do I have to unmute you?
Yeah, I can mention, I can put your slide link into Canvas if you want to.
Sure.
So people can have it at the same place. And I will try to play around a little bit with Duckytown. And maybe we also will run some raw OpenAI gym if it's required to keep the speed up. So we will check the details next week or something.
Yeah, Duckytown is the simulation environment. OpenAI Gym is the reinforcement learning algorithm. So you can I think in terms of teaching, you can start with tool examples in Gym and gradually move to Duckytown later.
Yeah, seems like a good idea.
So can anyone all unmute yourself? Sui, can you unmute yourself?
I think I'm unmuted. Not.
Oh, okay. I see someone. Let me see. Alan is okay. So I just wanted to make sure that you can do it yourself instead of me having to do the operation. Anyway, so any more questions?
No.
Okay, good. So today's agenda, I will give a grand tour of the major issues involved in autonomous driving AD. Subsequent lectures may dive into more details on each topic. First is the background and the processing pipeline from sensors and perception to planning and control, and HD maps, hardware platforms, software platforms, safety, security, ethical issues, and V2X communication. So this course is algorithms and systems for autonomous driving. So it's not just algorithms. I will discuss the systems aspect quite a bit. So what are autonomous vehicles? So they can refer to any type of autonomous mobile robot, not just self-driving cars. You can see Google's early version of self-driving car, and also drones, warehouse robots or indoor cleaning robots. Anything that moves autonomously can be called an autonomous vehicle. I will mainly focus on SDCs in the course, but many techniques for SDCs covered in this course are generally applicable to many other types of AVs. So why autonomous vehicles? I wrote down a few points off the top of my head, so you can add your thoughts. So reduced traffic accidents and fatalities. So in the USA, because the data from the USA is the most readily available, so I just picked out this data. In 2019, estimated 38,800 people lost their lives to car accidents. About 4.4 million people were injured. seriously enough to require medical attention in crashes. So AVs should be safer, theoretically. Reduced congestion and pollution. Yeah, when AVs are widely deployed, and passengers can have a more productive time spent on the road instead of driving, and autonomous mobility on demand with a fleet of autonomous vehicles is likely to become the low-cost, safe, and efficient mode of transportation that may make vehicle ownership obsolete. So this is the dream of Uber and many other companies. Uber, since its founding, it's been losing money every year, losing a lot of money every year because of the money they pay to the drivers. If they can get rid of the drivers, obviously it's very profitable to them. So it all started with advanced driver assistance systems. So since the initial introduction of cruise control in 1948, ADAS functions are increasingly prevalent in modern vehicles. So the common ones are adaptive cruise control, where you follow the leading vehicle at a fixed distance, anti-lock braking system, to avoid skidding on slippery road, a collision avoidance system, driver monitoring, where you will have an inward-looking camera monitoring the driver, electronic stability control to maintain stability of the vehicle, forward collision warning, lane departure warning, lane change assistance, surround view, etc. So there's a lot of ADAS functions today. So, but the real autonomous driving revolution started with 3 DARPA grand challenges. The first one was in 2004. It was held in the Mojave Desert region of the USA along a 150-mile route. None of the robot vehicles finished the route. Carnegie Mellon University's Red Team and Carl Sandstorm traveled the farthest distance, completing 12 kilometers of the course before getting hung up on a rock after making a switchback turn. So in this competition, no winner was declared, and the cash prize of $1 million was not given out. The next year, things are different. So the competition course this time is that vehicles passed through 3 narrow tunnels and negotiated more than 100 sharp left and right turns. 5 vehicles successfully completed the 212-kilometer course. Stanford Stanley vehicle won the $2 million top prize. In 2007, they held another challenge called Urban Challenge. So instead of the desert or the highway, they chose the site of the now closed Georgia Air Force Base. The course involved a 96-kilometer urban area course to be completed in less than 6 hours.
Songhua,
yeah.
Sorry to interrupt. Did you remember to record the session?
Yes.
Yeah,
I see
good.
this little red dot flashing on the top right. Is that right?
We can't see that, but you can hopefully. Yes, we can see that. That's
little
good.
Red dot.
Yeah, I see the red dot, and then you get a file, and then you can put it out on UMU Play, and then I can add a link in class.
So
Sorry
I forgot it when I started the lecture, so the first few minutes were not recorded.
Okay, thank you. Sorry for interrupting.
Sure. So the rules included obeying all the traffic regulations while negotiating with other traffic and obstacles and merging into traffic. So this time, Carnegie Mellon University's sports vehicle won the $2 million top prize, and Stanford's junior vehicle won the $1 million second prize. So these three grand challenge competitions jump-started the self-driving car industry. Faculty and students from winning teams such as Stanford and CMU later became leaders in SDC projects at companies like Google, Waymo, and Uber, and numerous startups. So economically, I think they figured out that holding these competitions is actually cheaper than providing funding for a SDC initiative, right? If you provide funding and each university gets, $500,000, you can't find so many universities. But if you provide cash prize, and universities fund themselves to participate in the competition, the strategy works pretty well. So just to mention why they have this urban challenge is because city driving is a more difficult task than highway driving. The table shows the comparison between highway driving and city driving. So traveling speed, obviously highway driving is high, city driving is low to medium. Traffic volume for highway driving is high, city is medium to high. Number of lanes, highways have lots of lanes, and city driving has a small number of lanes. And the difficult point for highway driving is the entry and exit points for traffic merging. That's where typically human assistance is needed. Once it's on the highway, typically the automated system can take over. For city driving, the challenge mainly lies in intersections where you need to turn with traffic lights. Yeah. So here's the brief history of SDCs being kickstarted in 2004, 2005, 2007 with the three DARPA grand challenges. 2009, Google begins its automated vehicle project, hiring a professor from Stanford who led the Stanford competition team as the head of the project. That's Sebastian Thrum. And 2012, Google's AV passes a 14-mile driving test in Nevada. 2013, Mercedes and Infiniti produced cars with radar sensors and some AD features. 2013, NHTSA, that's the United States National Highway Transportation Safety Administration, releases initial policy on AVs. And 2015, Tesla releases autopilot. So autopilot is not autonomous driving, it's ADAS, but more advanced ADAS. 2015, Uber hires 40 CMU robotics researchers to work on AVs, and Ford begins testing its AVs. 2016, lots of acquisitions and partnerships. General Motors acquired Cruise Automation. GM had a partnership with Lyft. Lyft is another company similar to Uber. Toyota had collaboration with J-Bridge Robotics. Uber collaborates with Volvo. And later, NHTSA issues guidelines for testing and deployment of AVs. And 2017, NHTSA issues revised safety guidelines for AVs. So the AV landscape today is getting very crowded. So there are literally hundreds of companies working on various aspects of AV. So including the autonomous vehicle manufacturers, that's the OEMs, and driving system suppliers. They provide subsystems components to the OEMs. data and simulation companies, and mapping companies. They provide high definition maps, and V2X communication companies, and LiDAR companies. LiDAR is a type of sensor which we'll discuss later. So it is a very vibrant topic today. So here's the AD patent applications issued in 2017. So we can see that Bosch, Audi, and Continental, the German firms, are leading in their number of patents applied, not granted. So because for patents, it's very slow. It takes 2 to 3 years to grant a patent application. So for patent application, it may be a more accurate measure of the current progress than patents granted. So the German firms have a strong presence in AD patents. It's maybe for 2 reasons. First, it's maybe easier to patent hardware than software components. Second, Bosch, Audi, and Continental have a history of registering many different variants of hardware patents. So that's what I read. I'm not sure if it's really true. So pure software companies, Waymo and Argo AI, they're leading companies in autonomous driving, but they're not even among the top 10 in patent applications. Hereby, the accuracy of interpreting the limited data available and extrapolating the true competitive positioning of automotive companies with registered patents may be limited. So here, Google, with 338 patent applications, number 10, so this does not include Waymo. So Waymo is not even on the list. So here's miles per disengagement. The California Department of Motor Vehicles defines a disengagement as a deactivation of the autonomous mode when a failure of the autonomous technology is detected, or when the test driver disengages the autonomous mode. So here Waymo is leading the pack with 11 miles driven per disengagement, between disengagements. And GM Cruise has 5 miles, and the Zoox and Neural, these are startup companies. But this is a flawed metric. There's a lot of disagreement on the level of accuracy of the metric. It's maybe too vague. It's valid only for California. So this data is only for California and may not reflect the difficulty of the chosen driving environment. So miles driven are not all equal. So highway miles are much easier to accumulate than urban miles. That's for 1 year of miles per disengagement. Here's the cumulative number of miles driven up to 2019. Waymo reaches 10 million miles, and Tesla Autopilot reaches 1 billion miles. It's because of their large user base of Tesla vehicles, and also because it is not really autonomous driving. It's ADAS. So when will AVs arrive? Here's a prediction from Emilio Frazzoli from Newtonomy, another AV startup. From 2017, so the red curve shows deployment in personally owned vehicles, and the green curve shows the mobility fleets, that is autonomous mobility on demand. It'll be first, it'll gain deployment in fleets starting from 2017 and gradually increasing the deployment up to 2040, when 75% of all vehicles should be autonomous. Personal owned vehicles will be much slower starting from 2025 with level 4 on the highways and slowly increasing as individuals purchase new self-driving cars. And yeah, so many people make many different types of predictions. So here's an interesting quote from Chris Urmson, co-founder, CEO of Aurora. So 2009, he said in 5 years, and then every few years he says in 5 years. So this shows the difficulty of the problem. So when the companies like Uber deployed autonomous vehicles with safety drivers, they thought that fully autonomous driving without safety drivers is coming soon, but it has turned out to be a much more difficult than most people expected. Right now, there are autonomous vehicles picking up passengers as taxis, but you'd have to have a human operator on board as a backup driver. So here's 5 levels of automation. Level 1 is ADAS. So they either control a steering or speed to support the driver. So the driver, human, should monitor the environment. You are the driver, even when automation features are turned on. So I'm not a frequent driver. I just find the adaptive cruise control is the most useful feature I used for ADAS. So especially if you're driving for a long time on the highway. So L2 autonomous automation is when both steering and acceleration are simultaneously handled by AD system. So the human driver still monitors the environment and supervises the support functions. So you can sit there and not touch the steering wheel and the acceleration and brake pedals, but you have to be alert and ready to take over anytime a warning is issued by the AD system. So this is where Tesla's autopilot is sitting. And then you can see a big gap from 2 to 3. It's because it is very difficult to go from level 2 to level 3. Level 3, conditional automation. The system can drive without the need for a human to monitor and respond. However, the system might ask a human to intervene, so the driver must be able to take control at all times. So the figure shows that the system is driving autonomously. The human can look at his phone. He doesn't have to pay full attention at all times, but there will be an alert when the system asks a human to intervene, and if so, the human must be able to take over control. So this is Tesla's autopilot is not at level 3 yet. So if you are playing video games while the car is driving, then it's not Tesla's responsibility if the car crashes. So Tesla is level 2. For level 4, these systems have high automation and can fully drive themselves under certain conditions. The vehicle won't drive if not all conditions are met. So for example, maybe it's a highway driving, clear weather, no rain, no snow. That's probably one condition that the AD system can take over. As soon as it starts to snow or rain, you get an alert. You have to take over control. Or if it's light traffic, with no obstructions, the car may be able to drive in the urban environment. But when it encounters some situation that doesn't know how to handle, like a construction site, like some kind of accident scene, and then a driver may have to take over control to pass the troublesome area, and then the automated driving system can take over again. So L4 is it's high automation. So the driver can sleep most of the time behind the wheels, but when something unexpected happens, he must be able to take over control. Finally, L5 is the Nirvana, is the full automation where the vehicle can drive whenever and wherever. So that's the dream of all AV companies. Yeah, so any questions on the 5 levels automation? Oh, sorry.
No, it's okay.
Okay. So state of the art, most current commercial products are at most level 2, like Tesla. From 2 to 3, it's perceived to be a giant leap. So automakers keep pushing the timeline of L3 and above to the future. So there are 2 different paths to L4 and 5. So Tesla, it starts from ADAS and mass deployment and gradually moves to level 4, 5. But Waymo, Nuautonomy, and many others are starting from L4 in limited geography and gradually expands deployment to mass deployment. So the goal is all the same, but the path are different. So the argument of Waymo, for example, is that Tesla's approach of requesting the driver to keep their hands on the wheel and be ready to take over control anytime is unrealistic. No human can do that for long distance driving. So drivers have been very creative in cheating the system, pushing down put something on the steering wheel to fool the autopilot, so the autopilot doesn't alert the driver, but you're just playing with the fire. So Waymo's view is that you should not trust the human to take over control. Instead, you should start from L4, and that's probably a safer route towards full automation. In fact, Tesla has had a few high-profile accidents where it is the driver's fault, where the driver did not put the hands on the wheels, and accident happened. So it's not Tesla's fault; it's the driver's fault.
Songwa?
Yeah.
I can mention I tried a Tesla some weeks ago, and running in snow was completely impossible. So it was really very far away from L5.
Yes, yes.
So here up in the north, it will be very difficult for them to even to detect the road or something, I guess.
Yes, snow is a challenge for everyone. Generally, AVs do not work in a snowy environment because snow covers all the landmarks, and you cannot do lane tracking. You cannot do localization. Everything breaks in snow.
Yeah, but I visited Scania, and they had a 3D scanner, so then they can kind of detect the road in snow also, so they can see where it was flat and see the diken just outside the road.
Yeah. So if you
so it's not impossible, but it was very expensive.
Yes, if you are talking about field robotics where you have robots driving in the wild without clear lane markings, then snow is not really a big issue. You just drive on the flat road. But for city driving, where you need to follow traffic rules, if you have snow covering the streets, it's not possible to drive.
Yeah.
So here are the 4 main tasks of an AV: localization, determining where am I, detection, to determine what's around me, and prediction to determine where are they going, where are the other objects going, including cars and pedestrians and cyclists, and finally planning and control, where should I go? So similar to how a human drives.
What about navigation? Is it the same as planning and control?
Yeah, I think navigation perhaps is another word for planning, isn't it?
Yeah.
I mean, navigation is not really a standard term for the self-driving car pipeline. The integrated navigation system, INS, is for localization. I guess.
Yeah, I was thinking maybe more about ships or something out on the sea where they navigate, they go to, US or something.
I guess it's a combination of localization and planning, I guess.
Yeah, it could be like that.
So here's the rough block diagram for the AV pipeline from sensor inputs to environment mapping, environment perception. So that green boxes are the sensing part to understand the surrounding environment, including localization, detection, and prediction. And then you do motion planning, decision making in the context of other road users. And then you do control, that's the acting, moving the car according to the planned trajectory. So focusing on the environment perception part, assuming that you already have the map, so you perform localization based on combination of GPS, IMU, and wheel odometry. So this involves sensor fusion and Kalman filters and other type of filters. And then you perform object detection, including static objects based on high definition maps, and dynamic objects on the road, including cars, pedestrians, and bicyclists. So when you detect objects, you draw bounding boxes around the object and perform dynamic object tracking. That is, detection is just static detection in the video frame. Tracking is to track the object across different frames across the timeline. And then based on the tracking, you can perform prediction. So where is this object going in the future? So the perception part includes localization and object detection. So a lot of the computer vision algorithms are used here, but also in combination with other sensors like LiDARs and IMUs. Prediction, so this is, there are two approaches. One is the Kalman filter and particle filter based prediction. Based on your recent past history, predict your near future, and also data-driven with machine learning-based classification. So the difficult part is pedestrian intention prediction based on polls and other information. So yeah, let's first look at the prediction. On the lower right, you can see that on the high definition map, where is this left car going, right? It has multiple possible choices. it may turn right, go straight, or turn into a left lane. And yeah, that's a prediction problem. A pedestrian prediction is very difficult because it involves understanding of the human's intention. So if a human is talking to a friend on the sidewalk, then he's not likely to be crossing the street, right? But if he's waving to a friend across the street, then he's very likely to be crossing the street. So you have to infer the human intention from the video, which is very difficult. So environment maps. So this is the mapping part with different types of maps. One is the occupancy grid map, where the environment is divided into a grid of small boxes, and some grids are occupied, some are free, some have a probability of being occupied. So that's the occupancy grid map. Localization map, where you can localize yourself, and detailed road map. That's the high definition map, where you have lanes and the traffic elements and everything on the map. So motion planning, it has 3 levels. One is mission planning. So it takes into consideration current goal, detailed roadmap, vehicle position, and computes a mission plan. So that is, it's really a high-level path planning problem, where, say, if you want to drive from home to your office, which roads should you take? That's mission planner. And behavior planner is to choose a behavior. Behavior might be turn left, turn right, and stop, and so on. A local planner is planning a local trajectory for example, passing a vehicle in front. So here's the more details on mission planning. So it's using graph search to find a path from source to a destination on the map. So from point 1 to point 0, you have multiple possible paths with different costs. The cost could be a distance, or could be a combination of distance and congestion levels. And then you need to find the minimum cost path through the graph. So that's mission planning. Behavior planning is to plan a set of high-level driving actions or maneuvers to safely achieve the driving mission under various driving conditions. So you can, for example, follow the leader in cruise control, decelerate to stop, or track speed or stop. So it's essentially a finite state machine with different behaviors in each state. A local planner is to plan a safe and smooth trajectory in a very short time scale. So trajectory is vehicle pose as a function of time. Pose refers to its XY position and also its orientation. So here the blue vehicle plans to pass the yellow vehicle on the right, the green vehicle on the right. So there are multiple possible trajectories. Obviously, these two are going on the sidewalks. They're not feasible, and these two may be too close to the front vehicle. And these 4 looks okay. They look perhaps okay, but maybe a little bit intrusive to the behind vehicle. So I think maybe these 2 on the right could be, and the blue path leading to this destination point could be good trajectories for this passing maneuver. notice that this trajectory is not a path. It's path plus time. It's path as a function of time. So for example, if you're looking at the mission planner, the path it's a geometry path on the graph. It doesn't have a notion of time. But here, the trajectory is a function of the xy point and orientation of time. It's because to avoid collisions and pass the vehicle, it's important to know the exact time of each point on the trajectory in order to avoid collisions, because the other vehicles are all moving. So I think it's time for us to take a short break. Let's reconvene at 2 o'clock.
Okay.
Zongguo,
Yes?
have you sent the Zoom link to the missing student, the PhD student at CS?
I thought, I'm not sure. I thought they did they register? I'm not sure.
Yeah, he's not. What was his name now? It was.
Let me see.
And there is another guy, Björn, who isn't online, but maybe he's. But at least he is in the site.
I just got an email from Marika Falk asking me if I have any students to be registered. Let me send her an email.
Yeah, we have all those students who are active on this course, if you see them in Camro. And then we have 3 who haven't logged in, the Ciali, Kielsa, and Kayo.
Okay, let me forward the email to you so you can I know this one guy, Michelle, but I'm not sure about the others.
And Team Anthony, is it the same as Antonio?
Who?
There is Team Anthony on this course, a student.
I don't know.
And on the video link, he mentioned himself, Antonio. Is that the same person? I think so.
Antonio is Leonard's postdoc, I think.
Yeah, is it also Team Anthony? Is it the same
No,
person?
I don't know.
No, you know, I am Anthony.
Okay.
Anthony, maybe it's other guy. I don't know.
Okay, so you are not Team Anthony.
No.
Okay, then we know. Sorry for mentioning your name.
Okay, it's okay.
Yeah. So I try to, but then we have some problems to add students in Canvas. We have to wait for the administration to do that. So maybe you should send the links to the slides and the Zoom to this guy at CS. I forgot his name. So I can see if I find him. So I can send a link to this student.
Okay.
So you can enjoy the rest of today.
Sure. Okay.
Thanks. Songhua? Songhua, I found his name Michele. So we send a link to him.
Okay, everybody back? Okay, so let's reconvene. So last time we stopped at local planner, where the vehicle plans a safe and smooth trajectory. That is, the vehicle pulls as a function of time. And finally, the controller. So the vehicle controller, there are two parts, velocity controller for longitudinal speed control and steering controller for lateral speed control. So velocity controller essentially controls throttle and brake for velocity. So common control algorithms include proportional integral derivative control and the model predictive control. There are others, but the industry uses only these two. So the controllers take into as input the planned trajectory and vehicle position, and tries to track the trajectory with control commands. Therefore, it's a good idea for the trajectory planner to the motion planner to take into account the dynamics, so that the trajectory is easier, it's feasible to track. It could be possible that the planned trajectory is had a really sharp turn that the vehicle cannot track at high speed. So the planner should be aware of the vehicle's capabilities. System supervisor is the supervision module that monitors the hardware and software component outputs to make sure that all systems are working as intended. It's also responsible for informing the safety driver of any problems found, including software supervisor and hardware supervisor. I will have a few examples of these later. So where does machine learning and deep learning come in? So the classic AD processing pipeline has a separate algorithms for each processing stage. You have one algorithm for perception, one for planning, one for control, and so on. So machine learning, deep learning have been making significant progress in recent years. The well-accepted approach is to use convolutional neural networks for perception, for object recognition, segmentation, and so on. So still in the early research stage is the approach with imitation learning or reinforcement learning, where you train a DNN, a deep neural network, so either end-to-end to map from pixels to control commands, or you have a hybrid approach with many variants of hybrid approaches, halfway mapping from pixels to waypoints, and then used for planning later. So there are many variants of this where to place the learning components. Several companies are making a bet on this IR approach, including Waymo, Voyage, Wavy, and so on. But the current industry practice, especially the traditional automotive OEMs, they are still conservative and relying on the classic AD processing pipeline, at most using convolutional neural networks for perception, but not for the other components. So just a little bit of animation. So this is use a CNN for perception, and then you may use a DNN for part of planning, and then you may use a DNN for end-to-end control. So here's the most difficult driving situation is unprotected left turn. So you can see that to turn left with no traffic signs or stop signs, you need to negotiate with the traffic. So traditional pipeline may work well in common driving scenarios. But in this kind of challenging scenarios, maybe IR approach may have advantages in this situation. So it must carefully yet swiftly navigate across lanes of oncoming traffic while acting in tandem with other fast-paced dynamic agents. If you're too conservative, you'll never make the turn. So the classic pipeline includes 4 steps. One is perception, to output a set of object detections, vehicles, pedestrians, within a certain radius of the self-driving car, which is then fed into prediction module. Prediction module uses present and previous observations to generate individual predictions about what each object may do in the next 5 seconds, and feeding all the predictions into an algorithm. A hypothesis can be generated about the safest action the AV can execute, and then finally it begins the prescribed maneuver and reassesses the situation every 100 milliseconds. So this classic approach may generate impressive and safe interactions, but it often results in an AV that's overly cautious when compared to a human driver, especially in dense urban environments. So what's missing is the concept of experience. So the classic pipeline, the prediction module will output the same set of predictions on drive number 1 versus drive 10,000 under identical circumstances. But if you have a learning-based approach with IL or RL, it may help alleviate this problem. You can gradually improve your predictions. So any questions on this overview of the pipeline part? Next part is the sensors and perception section.
No.
Okay, good. That's good. So let's move on to the sensors and perception. So perception is challenging. Here's a video from 2015 recorded by Google's AV.
Is a duck and a woman in an electric wheelchair with a broom chasing it in the road. So since then, we've seen people play Frogger with our car. Please don't. And then, you know, honestly, Austin kind of takes the cake. So here, we're at an intersection. That's 1, 2, and wait for it. That's 3 cars going the wrong way down the road, all at once. That was fantastic. We had this. Some dude comes out of nowhere, decides to roll on our hood, and then run away. And then this is great. So, you know, people are interested in our car and want to see how it reacts. So this guy was apparently so excited that he came running out without his clothes on. So really, I just want to say thank you, Austin, for keeping it weird.
Okay, so that's just a funny clip that Google's AV encountered. What is different situations that it encountered on the road. So if your classifier only knows about the traffic elements, then it'll be in trouble, right? So when you are doing deep learning training for classification, you have, say, 1,000 categories in ImageNet, right? And then what if different elements that's not in your 1,000 categories? Then the classifier will have no idea what that is. So that's the challenge of open domain classification.
Is a duck.
So here's the typical AV sensor configuration. Starting from the video cameras. Video camera detect the traffic lights, read road signs, keep track of the position of other vehicles, and look out for pedestrians and obstacles on the road. And then the the rotating thing is a LiDAR, bounces pulses of light off the surroundings. And then you have radars. Radar sensors monitor the position of other vehicles nearby. And you have rear radars on the rear. And then you have ultrasonic sensors for measuring the position of objects very close to the vehicle, such as curbs and other vehicles when parking. And for localization, you have GPS to provide positioning information. And then GPS itself is not very accurate, so you need to combine it with readings from other sensors to have a sensor fusion to provide more accurate localization. Yeah, that's the main sensors. And then finally, you have the central computer that typically for experimental vehicles is in the trunk. For production vehicles, it may be placed somewhere else. So it's a central computer that manipulates the steering, acceleration, and brakes. Yeah. So here's the configuration of sensors of some research AVs. I collected this data from various sources on the internet. For example, Uber's car has 8 cameras, 1 LiDAR, 4 radars, and GM Cruise has 16 cameras, and so on. Tesla has 8 cameras, no LiDAR, and 1 radar. So Tesla, notably, is the only OEM that does not use LiDAR in its AV. So Elon Musk said in 2017 in my view, it is a crutch that will drive companies to a local maximum that they will find very hard to get out of. Perhaps I'm wrong and I will look like a fool, but I'm quite certain that I'm not. So Mobileye also shares this view and advocates using cameras only. So my opinion is that the cameras theoretically should be enough, since that's the human sensing modality. Humans drive quite well with their eyes as the only sensor, but in practice, computer vision algorithms are not yet at the level of human visual system, eyes plus brain, and LiDAR can be very helpful. So I think one reason that Tesla does not use LiDAR is to save cost. So even though computer vision has been advancing very fast, you have ResNet, all kinds of nets that's breaking records on ImageNet competition. Still, in the highly complex open domain situation like driving, is not adequate. So passive versus active sensors. So cameras are passive sensors. They detect existing energy like light radiation reflecting from objects in the environment. So it relies on environment lighting. It doesn't work in the dark. Active sensors, also called range sensors, send their own signal and sense its reflection. So LiDAR, radar, ultrasound, these are active sensors. They do not rely on environmental lighting. So here's the wavelengths of different sensors. Cameras use visible light spectrum, and LiDAR uses the 10 to the minus 6. And thermal cameras, these are night vision cameras that allows you to see in the dark. And radar, 10 to the minus 4, will use these microwaves. Okay, so camera is the most versatile sensor. It's the main sensing modality of humans. And if you have two cameras, you can generate a stereo view, just like human eyes. So the key parameters include resolution. So if you have 1080p HD camera, you can provide 1920 times 1080 pixel resolution, or 2.1 megapixels. Field of view is the extent of the observable world that's seen at any given moment. That's the angle of view. So given the same resolution, a wider FOV results in larger image distortion, which is obvious if you are a photographer. Dynamic range is the maximum difference between the darkest and lightest pixel intensities in the image, measured in stops. So an increase of 1 stop equals a doubling of the brightness level. So HDR, high dynamic range cameras, are standard in modern smartphones. So range sensors rely on time of flight, TOF, to measure distance or range, which is a key element for localization and environment modeling. So LiDARs use electromagnetic waves. Ultrasonic sensors use sound waves, and radar sensors use radio waves. So the traveled distance of a wave is given by this formula: d, distance, equals velocity, the speed of wave propagation, times the round trip time, TOF, divided by 2. So yeah, as shown in the figure. it's quite obvious, right? So the range sensor, different sensors have different propagation speeds, v. So the sound travels 0.3 meters per millisecond. Electromagnetic wave, like including light, travels 0.3 meters per nanosecond, 1 million times faster than sound. So to travel 3 meters, it takes 10 milliseconds for ultrasonic and 10 nanoseconds for LiDAR. So measuring time of flight, TOF, with electromagnetic signals is not an easy task. Hence, LiDARs are expensive and delicate. Okay, so the quality of range sensors mainly depends on inaccuracies in the time of flight measurement. For laser range sensors, opening angle of the transmitted beam. For ultrasonic range sensors, interaction with the target depending on the surface of the target, and variation of propagation speed, and speed of vehicle and target. Okay, so LiDAR, light detection and ranging device, sends millions of light pulses per second in a well-designed pattern to generate point clouds that describe the 3D geometry of the surrounding environment. So the figure shows the point clouds generated by a LiDAR sensor. The key parameters include the laser beam count, point cloud per second, how many points in the cloud, rotation speed, field of view, and range distance from tens to hundreds of meters. So here's the Velodyne LiDAR. So the high-end model of HDL64E has 64 laser emitters, rotation up to 15 Hertz. That's 15 rotations per second. Field of view is 360 degrees horizontally because it rotates around, right? And 26 degrees vertically because the light beams can be horizontal or slanted upwards or slanted downwards. So that's the 26.8 degrees vertical field of view. Angular resolution is 0.09 for horizontal resolution and 0.4 for vertical resolution. Delivers 1.3 million data points per second. It is very expensive, $40,000 to $80,000 US dollars. This is the high-end model. You have cheaper versions available with a smaller number of laser emitters and other parameters. So you can see it's very distinctive. It sits on top of the vehicle. So it rotates very fast at a very fast speed. So one point is that its position on the top increases the air resistance and reduces mileage. So that is a real issue, but it may be a minor concern right now.
Songhua?
Yeah.
I read somewhere that they are really decreasing in price, these LiDARs.
Yes.
There will be, so really divide by 10 each year or each 5 years or something. Yeah.
Yeah, on the next slide, I show the situation in 2018 where the Velodyne LiDAR is a mechanical device. It rotates physically, and then many other companies, I think right now there's over 100 LiDAR companies now making solid state LiDAR with various different technologies. That's they got rid of moving parts, which makes it much more power efficient. And all these variants, I don't understand each one of them, but the point is that there are many vendors in the market today. Velodyne is an early pioneer, and it has the highest quality, but may not be so in the future. And also, LiDAR is not just for autonomous driving. It's used for many other scenarios: space, topography, wind, transportation, robotics, consumer, and so on. So a millimeter wave radar is for accurate target detection and relative speed measurement. So as you know from biology class, it's the main sensing modality of bats. So the key parameters are sensing distance, field of view, position, and velocity accuracy. There are two types: short range, short to medium range with a wide field of view, and long range with a narrow field of view. So ultrasound is mainly used for parking assistance. Short sensing range not affected by lighting condition, rain or fog. The key parameters are sensing range and field of view. So it's very inconspicuous, unlike a LiDAR. So it sits like this. It's a very small opening in the car. And you may have front and side ultrasound for parking assistance.
I can mention an anecdote if you want.
Sure.
I was working with Mercedes and BMW some years ago, and they didn't like this little hole in the car. So instead of ultrasound, they were using 7mm radar equipment, which they can hide behind. So it was not visible from the outside. The car had a radar parking assistant. So they can park elegantly without any holes in the car. So it's more for beauty or hiding.
Yeah, that's interesting.
Yeah.
Thank you for the discussion. So anyone else who wants to chime in with any discussions, you're very much welcome. So here's the comparison chart of the sensing ranges of different sensors. The round thing, something wrong with my pointer. Whenever I draw something, it has something turning to the left. It works okay now. Okay, anyway, so the round thing is LiDAR, because LiDAR rotates and senses the environment in the 360-degree field of view. So it's for 3D environment mapping, object detection. Cameras, you have front, rear, side cameras. A combination of cameras for short, long-range object detection. It's the most versatile sensor from distant feature perception to cross-traffic detection, road sign detection, and so on. And then radar, you have long-range radar for object detection through rain, fog, dust. And the short-range, medium-range radar for including side and rear collision avoidance. So the radar for parking that you mentioned may be the short-range radar, and then the long-range radar could be used for collision avoidance, even on the highway. And ultrasound is very short-range sensing. Here, it's mainly for close-range object detection, for object entering your lane or for parking. So this figure gives an intuitive feel for the ranges of different sensors. So on the bottom, the link here is this autonomous vehicle technology report, which I highly recommend you to read in your spare time. I also uploaded this document in Canvas. So each sensor has its strengths and weaknesses. Sensor fusion can achieve the best result combining the different sensors. So for sensing range, radar has the best range. Long-range radar can sense very far, functional in bad weather. So camera is poor. You cannot see in bad weather very well. Radar is good. Functioning in poor lighting. Camera is mixed. Depending on how poor the lighting is, you have your headlights, of course, and LiDAR and radar are good. Object detection. So LiDAR is very good. Camera and radar are mixed, depending on the environment conditions. Classification, camera is good because camera captures the most information of the environment, including the color, the shape, texture. So a lot of the information can be used for classification, whereas LiDAR only gives you point clouds. You know there's a cloud of points over there, but you don't know exactly what that is. So it's much harder to do classification with LiDAR point clouds. It's much easier with camera images. And radar, you can only detect there's obstacle there. You don't get any much more information than that. You get the distance, the speed of the obstacle. You don't know anything about any other information about the obstacle. So the classification part is very weak for radar. Lane tracking, it's good for camera. Computer vision algorithms, including deep learning or classic computer vision, are very good at tracking lanes and not very good for LiDAR and radar. So by a combination of different sensing modalities and with sensor fusion algorithms, you can achieve the best of all the different, you can combine the benefits, combine the strengths of different sensors. Integrated navigation system, it's typically a combination of GNSS, Global Navigation Satellite System, and IMU, Inertial Measurement System. So GNSS measures position and velocity with satellites. Common GNSS systems include the GPS, which is the most popular one from the United States, Galileo from Europe, Beidou from China, and GLONASS from Russia. So I think everyone knows GPS, but Beidou has achieved some commercial deployment in China. Many smartphones are equipped with Beidou in addition to GPS. I think Galileo is primarily used for scientific research, not really deployed commercially. IMU measures acceleration, the linear or angular acceleration, and orientation. That's a yaw, pitch, and roll. So here's the airplane illustrating the concepts of, so a yaw is turning your head to the left or right. Pitch is when you perform a up and down pitch of your airplane head, and roll is to rotate around the your vehicle axle. So for ground vehicles on 2D plane, only yaw is irrelevant, but for aero vehicles in 3D plane, all three are relevant. So INS is a combination of GNSS and IMU for localization. Wheel encoders, they measure the distance traveled by counting the number of wheel rotations and multiplying it with the circumference of the wheel. So the accuracy is affected by slippery road conditions, road surface, which causes tire to move without rotation, and also severely worn tires, which affect the tire circumference. So that's the wheel odometer. That's how the mileage in your car is computed. It's shown on your dashboard. And the structured light sensors, these are active sensors that emit a structured light, a pattern of light. It's typically used for indoor robots because outdoors, because of the sunshine, the structured light really doesn't work. So they project a structured light on the scene, and reflected light is perceived by the camera. So arranged to the illuminated point can be determined from geometry. So here's the example. So on the right, you see different patterns of light. Could be a bunch of dots, could be some lines, could be a grid, and so on. So Microsoft Kinect is very widely used structured light sensor. So it has infrared IR projector, project infrared light on the environment in a particular pattern, and also a VGA regular camera, and microphone array, and so on. So it's used to be used widely for indoor robots, but I think they stopped production of this particular product. So event cameras, they are also known as a neuromorphic camera. So silicon retina or dynamic vision sensor, all different names for the same thing. So these are imaging sensor that responds to local changes in brightness. So they do not capture images using a shutter as in conventional cameras do. Instead, each pixel inside an event camera operates independently and asynchronously, reporting changes in brightness as they occur and staying silent otherwise. So they can have a microsecond resolution, temporal resolution with a low delay rate, and do not suffer under overexposure or motion blur. So motion figure below shows the output from a conventional frame-based camera versus a event camera for rotating fan. So the conventional frame camera, because the shutter speed is not enough, it has a severe motion blur. But the event camera only detects moving parts, so it emits a bunch of points that's very accurate with crisper edges for rapidly moving objects. So right now it's mainly used for vision of high-speed drones. So I have not seen any commercial applications for ground autonomous vehicles, even though some companies are pushing for it. Let's watch a video from a company that sells these kind of products. Let me figure out how to share my browser. Okay, suppose disable share sound, breakout, manage, new share. Yes. I think there's no sound. Yeah, here you can see the output from the event camera. So it only detects moving parts. So as long as the children are moving, you can see the green and red dots. Green is you detect the object moving to the right, and then red is that the object is disappearing, is moving away from the camera. That's traffic counting, where you can count the traffic. A number plate reading. And tracking of a high-speed LED marker. High-speed robotics. Event-based SLAM. Yeah, here you can see on the right is what the event camera sees. So anything that moves can be captured by the event camera. Okay, so we have discussed the different types of sensors. So any questions?
I can mention also, if you haven't noticed, you can press at the bottom, Manage Participants, and then you see a list of your own, and then you can kind of raise your hand or something. So then we will see that on the videos. If you don't want to interrupt Songhua while he's speaking, then you can just, like me, I can say yes, something, and then we will see this yes.
Well, did you type yes somewhere?
No, if in the bottom there is a Manage Participants.
Okay.
And there, if you press that button, you will have a list of participants up to the right.
Yes, I see it.
And then you can click your own name or so. But there are buttons like yes, no, go slower, go faster, and more, like coffee break or something.
I see.
And then
Yes,
I
yes.
see my coffee break symbol or tea break maybe. So there's a way without, if you need to ask something, then someone can see that and then make a short break to give you a chance. And also there's a reactions down to the right where you can push a clap or something or thumbs up like this.
Oh, okay.
So if you want to respond a little bit to the speaker, that would be kind.
So I just did an unmute all. I'm not sure it works. It says all participants are unmuted, but it still shows muted.
Yeah, I got unmuted.
No,
Okay.
not all of them. Alan and Alexander is still muted.
It's for me.
We get like a box appearing and asking us if you would like to unmute.
Ah, okay. So you can choose.
You can.
Okay.
Yeah. Maybe you're listening to rock and roll at home. So,
So you will never know. Yes.
And we welcome also Michele, who is with us now as a
Hi.
PhD student from CS.
oh, okay.
Hi.
Do you pronounce Michele or Michele? Or...
Michele. Michele is the correct way. Yes.
Oh, thank you.
So let's move on to our perception. The four main perception tasks are detection, detecting the existence of an object in the environment, classification, identify what the object is, traffic sign traffic light, pedestrian, and so on. Tracking is to track a moving object across time, and segmentation, also called the semantic segmentation, is to classify each pixel to its semantic category, like road, car, sky. So here you have a color for the road and a red, purple for the sky, and so on. So here's the Mobileye's autonomous car showing what the system sees. So you can see that they did a segmentation of the road. The green part is the road, but they didn't care about the buildings on the side. They didn't bother to segment these parts. Also, they did object detection with the red boxes indicating pedestrians and green boxes indicating vehicles. This little green blue thing, I think that's the center of the lane.
Nice with the green streets as well.
Yeah. Oh. So AV sensors generate big data. So this is an image from Intel. So the most amounts of data is generated by cameras and LiDARs. So cameras generate 20 to 40 megabytes per second, depending on how many cameras you have and the resolution of each camera. And LiDARs generate 10 to 70 megabytes per second, again, depending on the LiDAR's resolution and number of emitters. So other sensors generate much less data. So radar generates a few hundred kilobytes, 10 to 100 kilobytes. Sonar generates 10 to 100 kilobytes per second, and GPS generates 50 kilobytes per second. So if you drive it all day, you get 4,000 gigabytes per day, and then all these data must be processed in real time by perception algorithms. So in terms of computer vision, the OpenCV library implements many of the classic non-machine learning CV algorithms. So including the core operations, that's the basic operations on images like pixel editing, geometric transformations, code optimization, some mathematical tools, image processing, that's for thresholding, smoothing, edge detection, hue line transform, Hoffline transform, and feature detection and description. That's a hog, sift, surf, brief, orb, many different descriptors. Video analysis for object tracking with optical flow, camera calibration, and 3D reconstruction. So they are very simple, fast, and reliable, especially for lane detection. You don't need deep learning for lane detection. So they're often used in conjunction with complex machine learning, deep learning algorithms, which may be sometimes unreliable and unpredictable. So especially for deep learning, because of the complexity of the deep neural networks, you may have unexpected results sometimes. But these simple classic vision algorithms are very reliable. So you'll be surprised as how they are widely used in autonomous vehicles. So deep learning have not really killed all computer vision algorithms as somebody may claim. These reliable vision algorithms are still very much widely used. Machine learning algorithms, they enable computers to learn from data and perform certain intelligent tasks. Machine learning taxonomy. First is supervised learning, where the system is presented with example inputs, the desired outputs, and the goal is to learn a general rule that maps inputs to outputs. They include a classification to classify an image, to tell if it's a cat or a dog, regression. For example, you can predict housing price next year. Unsupervised learning is more challenging, where no labels are given to the learning algorithm, leaving it on its own to find structure in its input. You can discover hidden patterns in data, or you can do feature learning. That means towards an end, feature learning can be used in later stages with supervised learning. There are parametric unsupervised learning, for example, Gaussian mixture models, and non-parametric unsupervised learning. Reinforcement learning is when an agent interacts with a dynamic environment in which it must perform a certain goal. The agent is provided a feedback in terms of rewards, and it tries to learn an optimal policy that maximizes its cumulative rewards. The algorithms include model-based and model-free. So model-based, a model here refers to a model of the environment. So if you issue an action to the environment, how does it respond? How does it evolve in response to the action? Model-free is when you have no model for the environment. For model-free, you have value-based and policy-based. Applications include game playing. AlphaGo is the most well-known example, robotics and autonomous driving. So the basic idea of deep learning is to have a deep neural network with many hidden layers to extract increasingly abstract features layer by layer until the last layer produces a classification result. So here's a image of a DNN where you have inputs from the left, and you go through a bunch of hidden layers, and eventually from the output, you have a classification result from O1 to OM. And then on the lower part, you see the different features extracted from the input image. From a input image of pixels, you can extract the edges, the simple edges. And then you can extract increasingly more complex features as you go through the intermediate hidden layers. And finally, you can extract features that look like a human face. Eventually, you put a classification layer on top of the features. You can detect and identify the human face. So let me see. Okay, I think it's time for another break. We'll take a 5-minute break until 3 o'clock. I know it's a long afternoon for 4 hours, so bear with me.
Yeah, hello, sorry, Songwa.
Yes.
Yeah, I'm sorry, but I have to leave for my other lessons at 5:15
Sure.
to 17.
Yes.
But I noticed your recording. Maybe you should kind of stop the recording for each hour and then have, otherwise you might lose everything if it's a power supply failure or something, whatever.
To click on the red dot or?
stop recording, and then I guess you will get some question about where to save a file or something.
Are you planning, Zonko, are you planning to have this video also posted somewhere?
Yes, on UMU Play.
So there will be link somewhere.
Yes, yes.
Okay, okay, thanks.
Stop recording. Should I pause or stop?
I guess if you stop, you will get a question or where